In this session, I will talk about the meta-analysis of diagnostic studies. What is a diagnostic study? The purpose of a diagnostic study is to evaluate the quality of a diagnostic test. So think, for instance, of a self-test for corona. You hope that your test can make a distinction between people who are positive and people who are not positive. In diagnostic studies, often multiple tests are compared to each other, but it's also possible that only one specific test is studied. What kind of data reported in a diagnostic test study? Well, if we want to say something about the quality of a diagnostic test, we need to have a standard, or we need to have a criterion to decide on whether a person is positive or not. And we use that criterion to see whether our test that we want to evaluate works well. So let's look at the cases that are positive. We hope that with our test, most of these cases that are positive are also positively tested. So we hope that the cases that are truly positive is as high as possible compared to the cases that are positive but that are not positively tested. So these cases are called false negatives. So we hope that the true positives is larger than the false negative number. Similarly, for the cases that are in reality negative, we hope that most of them are tested negatively. So these cases are called true negatives, and that there are only a few or none cases that are positively tested. So these cases are called false positives. So in general, we hope that the dark blue and the dark red cell include as many cases as possible, and that the other two cells include as few cases as possible. So think, for instance, of an instrument, a screening instrument for the Down syndrome. So suppose that in a study, we have data from about 5,000 persons, 5,000 babies. Some of them are positive, so some of them show Down syndrome, more specifically about 10 persons, and the other persons are not positive. So suppose that these 5,000 babies were also screened previously, so during the pregnancy, and that from the 10 positive cases, 9 cases were positively tested using the screening instrument, and one of them was not detected using the screening instrument. From all the negative cases, so there are 4,800 negative cases. From all these negative cases, most of them were tested negatively based on the screening instrument, which is good, but 351 cases were tested positively. So of course, both errors are not desirable. So if a specific baby has the Down syndrome and this was not detected using the screening instrument, this has negative consequences. For instance, maybe the parents would have decided to abort the baby, or maybe it has negative consequences in the sense that the parents are not prepared at all for having a baby with Down syndrome. The other type of error, so the negative and the cases that were tested positive, whereas in fact these babies did not have the Down syndrome, also is not desirable. This induces unnecessary stress for the parents, So if parents are told that maybe the baby that I will get will have the Down syndrome, whereas in fact this is not true, this induces unnecessary stress. A measure that we can use to express the quality of the screening instrument is the odds ratio. Here we can talk about the diagnostic odds ratio. We have already seen the odds ratio as a measure of association between two dichotomous variables. So we can use this measure here as well. The odds ratio can be calculated by multiplying the true positives and the true negatives, so that are the dark red and the dark blue cells, and we divide this multiplication by the false positives multiplied by the false negatives. So these are the two kinds of cases for which we made a wrong decision. The diagnostic odds ratio in the example is 114.08. Note that there will be no association between the two variables if the odds ratio is equal to 1. So here the odds ratio is clearly much higher than 1. An odds ratio of 1 would mean that the screening instrument does not say anything about whether or not a case is positive. We've also seen that a drawback of the odds ratio is that it has a skewed distribution. It's also not very handy that the absence of an effect, the absence of an association, means that the odds ratio would be equal to 1. It's easier if the measure of association would be equal to 0 if there is no association at all. Another drawback of the odds ratio is that the sampling variance is not easily calculated. So therefore, very often the natural logarithm of the odds ratio is taken. So we use the log odds ratio. In this example, the log odds ratio is 4.74. A log odds ratio equal to 0 means that there is no association at all. So again, here we see that there is evidence that the screening instrument seems to work. The sampling variance of the log odds ratio can be calculated by taking 1 over the sample size in the first cell plus 1 over the sample size in the second cell, and so on. And so in our example, this gives a sampling variance of 1.11. We can use that sampling variance to calculate a confidence interval around the log odds ratio. The sampling distribution of the log odds ratio is more or less a normal distribution. So we can calculate the confidence interval, or 95% confidence interval, by taking the mean or the estimate of the log odds ratio and subtracting or adding 1.96 times the square root of the sampling variance. This gives us confidence interval starting from 2.67 going to 6.81. 0 is not included in the confidence interval, so again here it's clear that there is an association between the two variables, or in other words, that the screening instrument says something about being positive or not. Remark, suppose that one of the cells does not include cases, or that in one of the cells the number is equal to 0. In that case, you cannot calculate the odds ratio and or the sampling variance of the odds ratio. So a solution that is often used is that you can add 0.5 to all of the 4 cells to avoid that in one of the cells you have 0. Now suppose that you have a sample of studies, of diagnostic studies, and in each of these studies you have an odds ratio, or you can calculate an odds ratio. How can you combine the data from these studies? Well, we can combine these diagnostic odds ratios, or more specifically, we can combine the log odds ratios using ordinary precision weighted meta-analytic techniques that we have seen before. You can also, if in some of the studies odds ratios are calculated, but in other studies you have standardized mean differences, we have seen that you can convert log odds ratios to standardized mean differences using this formula. So the standardized mean difference is equal to the log odds ratio multiplied by the square root of 3 divided by pi. And so this means that you have to multiply the sampling variance of the log odds ratio by 3 divided by pi squared to obtain the sampling variance of the standardized mean difference. Of course, you can also calculate log odds ratios based on standardized mean differences, so convert measures in the other direction. When are you going to use log odds ratios in your meta-analysis? When are you going to use standardized mean differences? So you can choose between these two options, but a good idea is to use the effect size that is more commonly used in our set of studies. So if you have 10 studies in which a log odds ratio can immediately be calculated, and one study in which a standardized mean difference is reported, then it makes sense to convert that one standardized mean difference to the log odds ratio. Note that by calculating an odds ratio or log odds ratio, you lose some information, in the sense that it's possible that different kind of tables will give exactly the same odds ratio and therefore also the same log odds ratio. So you lose information that is included in your table by calculating the odds ratio. Can we avoid losing information? Yes, we can. It is possible to calculate two measures of quality instead of that one measure, the odds ratio. More specifically, we can calculate the sensitivity and the specificity. What is the sensitivity? The sensitivity is the number of true positives divided by the total number of positives. So here in the example, we have 10 positive cases and 9 of them were detected using the screening instrument. So that means that the sensitivity is 90%. So it's the probability that a positive case will be tested positively. The specificity is the number of true negatives divided by the total number of negative cases. So in our example, there were 4,800 negative cases, and 4,449 of these cases were indeed tested negatively. So that means that for 93% of the negative cases, these cases were tested negatively. So we hope that both the sensitivity and the specificity are as high as possible. Note 93% of the negative cases were tested negatively. So this means that 7% of the negative cases were tested positively. So this is called the false positive rate. The false positive rate is the probability that a negative case is still tested positively. What is also sometimes reported in diagnostic studies is the likelihood ratio for cases that were positively tested and a likelihood ratio for cases that were negatively tested. What is that likelihood ratio for positively tested cases? Well, that's the probability that a positive case is tested positively. So that's the sensitivity divided by the probability that a negative case is tested positively. So that's 1 minus the specificity. And the likelihood ratio for the negatively tested cases is the probability of a positive case tested negatively divided by the probability of a negative case tested negatively. So it's 1 minus the sensitivity divided by the specificity. And the ratio between that likelihood ratio for the positively tested cases divided by the likelihood ratio for the cases that are negatively tested, that ratio is another way of calculating the diagnostic odds ratio. Now, instead of doing a meta-analysis of the diagnostic odds ratios, it's also possible to do meta-analysis of the sensitivity and the specificity values. One way is to do two separate meta-analyses. So again, using precision weighted analysis, but separately for the sensitivity values and the specificity values. Another approach, which is somewhat more efficient, is to use a bivariate meta-analysis. So how does it work? Well, we say that the number of positive test results for positive cases in study I and the number of positive test results for negative cases in study I, these two numbers follow binomial distributions. So the number of positive test results for positive cases in study I follow a binomial distribution with the number of positive cases and with a probability, so the probability that a positive case is tested positively, so that's the sensitivity. For the negative cases, the probability of that binomial distribution is the false positive rate, so 1 minus the specificity. So that's the probability that a negative case will be tested positively. And then we say, well, these two probabilities, so the sensitivity and the false positive rate, they follow a normal distribution across studies with means theta 1 and theta 2. So theta 1 is the overall sensitivity across all studies, and the U1I is the random effect of study I for the sensitivity. So if that is positive, then this means that the true sensitivity for study I is larger than the mean sensitivity across all studies. The same is true for the false positive rate. So theta 2 is the overall false positive rate across all studies, and the U2I is the random deviation for study I. So if that is positive, then the false positive rate for that study, or the true false positive rate for that study, is larger than the overall false positive rate. And we assume that both random effects follow a normal distribution, a multivariate normal distribution with means 0 and with variances and a covariance that should be estimated. So now, we use a multivariate or a bivariate meta-analysis. So now we have two between study variances. So the between study variance in the sensitivity rate and the between study variance in the false positive rate. And there is possibly a covariance between the two parameters across studies. Note the sensitivity and the specificity that is found in a specific study depends on the cutoff or the threshold that is used in that study. So suppose that you have a test value, and that when the value exceeds a specific value, the threshold, you conclude, okay, that case is positive. When that person or the test value does not exceed the threshold, then that person is called a negative case. Well, and suppose that you have in reality, so two normal distributions of these test values. The blue distribution is a distribution of the negative cases, so the really negative cases. The red distribution is the distribution of the cases that are in reality positive. And you can see that part of the negative cases have a value that is larger than the threshold. So that's the light blue surface. So these are the false positives. You can also see that from all positive cases, so that's the right normal distribution, part of them has a value lower than the threshold. So these cases are not tested positively, whereas they are positive. So these are the false negatives. So that part is given in light red. Note that by increasing the threshold, so by moving the green line to the right, the number of false positives will become smaller. So this means that the specificity that is found in that study will become higher. At the same time, there will be more false negatives. So the light red surface will become larger. So this means that the sensitivity will become lower. So by increasing the green line, you increase the specificity, which is good, but at the same time, you decrease the sensitivity, which is not good. So therefore, you can expect that there is an association between the specificity and the sensitivity, so that there is a covariance. So in the previous slide, I explained that we can estimate the covariance between specificity and sensitivity. Well, in fact, we can expect that there is a negative association between the two measures because different studies can use different thresholds. And so studies using a very large threshold will probably have a higher specificity rate, but a lower sensitivity rate. So the sensitivity and the specificity depend on the cutoff used. So this means that the results of the meta-analysis are not that interesting, in the sense that variances in specificity and sensitivity may not reflect true differences between the study findings, but may rather reflect the difference between studies in the threshold that is used. As an alternative approach, which is, however, statistically equivalent, you can also use the receiving operating characteristic curves, so the ROC curves. So a ROC curve summarizes the data per study or possibly over studies. So a ROC curve looks like this. So on the y-axis, you have the sensitivity. On the x-axis, you have this 1 minus the specificity. So on the y-axis, you have the probability that positive cases are tested positively. On the x-axis, you have the probability that negative cases are tested positively. So you hope that a study will find, and for each study, you can calculate these two measures, and you hope that the sensitivity will be as high as possible, and the 1 minus the specificity will be as small as possible. But you can expect that there is a relationship between the two. So the higher the sensitivity, the lower the specificity, and therefore also the higher 1 minus the specificity. Now, suppose that, so here you can see the results of multiple studies. Each dot stands for one specific study. All these studies studied one specific instrument. So all these data together give some evidence that that instrument seems to work. If the instrument does not work at all, then the dots would be scattered around that diagonal line. More specifically, then you would expect that the probability that positive cases are tested positively is exactly the same as the probability that negative cases are positively tested. So in that case, the dots would be distributed around that diagonal line. But here you can see that the majority of the dots are higher than that diagonal line. So which means that even if given a specific specificity, sensitivity, 1 minus the specificity is smaller. So this is what we hope to find. You can go to that site from which I have put the link on the slide to play around with the threshold, and you can see indeed that if you change the threshold, then you would expect to find another sensitivity and another 1 minus specificity. And so that curve that is given in that plot describes how the sensitivity and the specificity are related to each other, and the values depend on the threshold that is used. So based on that curve, you can find the best solution. You can think about what is the cost of making one specific error and the cost of making another type of error. For instance, what is the cost of not finding a positive case versus what is the cost of saying that the case is positive, whereas that case is not positive. And by balancing these two costs, you can decide on what threshold you could use. Note that the second plot here looks better than the first plot. In the second plot, the instrument seems to be able better to make a distinction between these two distributions. So whereas in the first plot, in the upper plot, there is a large part or large surface of false positives and false negatives. In the plot at the bottom, it's clear that these two surfaces are much smaller. This is also reflected in the ROC curve. You can see that here the ROC curve is much higher, is much farther away from the diagonal line. A measure that can be used to express how good the instrument is the area under the curve. So the area under the diagonal line would be 0.50. So the area under the curve for the instrument at the upper plot is 0.73. For the under plot, it is almost 1. So you can see that there's only a small part of the total surface that is on the left side of the curve. So you hope that that curve, that area is as large as possible. Ideally, this equal to 1. So the higher the area under the curve, the better. Now, how can you meta-analyze ROC curves? Well, you can use this model. So at the lowest level, so within studies, we have the same equations as before. So we say that the number of positively tested cases, given that cases are positive, follow a binomial distribution with number of positive cases and with a specific sensitivity rate. The number of positively tested negative cases, it follows a binomial distribution with the number of negative cases in that study and with a probability that is equal to 1 minus specificity. And then we say, well, these two probabilities, so these two pi's, can be described as a nonlinear function of theta I plus alpha I times xij times x minus beta xij. So there are two probabilities. So pi 1i and pi 2i. So the j in the equation of level 2 refers to positive subjects or negative subjects. And the xij is equal to 1 for positive subjects and 0 for negative subjects. And then the parameters that are estimated in our meta-analysis are the means of the theta i's and the alpha i's, as well as the variances and the covariances across studies of these two parameters. But what are the meanings of these parameters? Well, so suppose that you have so xij is equal to 1 for positive cases and 0 for negative cases. So for negative cases, the equation simplifies a lot. So for negative cases, the logit of pi is equal to theta I. So theta I determines the probability for a negative person of being tested positively. So that refers to the threshold used in the study. And so the variance in the theta i's refers to the differences between studies in the threshold that is used. Alpha I, so which is a parameter for study I, indicates to what extent the probability for testing positively changes when a person in reality is positive and not negative. So it refers to the discrimination of the test. So we hope that alpha I is as high as possible. So alpha I refers to the quality of the test. And what is the meaning of beta? So you can see that in the graph. So in the graph you can see, look first at the red and the blue curve. So the blue curve is for a test that discriminates not at all. So for a test with a quality of 0, so alpha is equal to 0, whereas for the red curve, alpha is equal to 2. You can see that it's better, the higher alpha, the better the test discriminates between the two groups, between true positives and true negatives. What's the meaning of beta? Well, compare the red and the gray curve. Well, the red curve is a symmetric curve, whereas the gray curve is an asymmetric curve. So the beta describes or expresses the asymmetry of the ROC curve.